All right. Hello, everyone, my captive audience. Today, we are here to talk to you about live super resolution on Twitch. Scaler of today, here today. I'm John Bartos, an engineer at Twitch, and this is James Hurley, also an engineer at Twitch. Now, for those of you who are Demuxed OGs, who may have been here in 2019, you may already know what super resolution is. Nick Chadwick did a talk about how you can use machine learning to upscale and enhance images with quality better than what you would get with a typical bicubic or Lanczos upscaler. This talk is not going to be what Nick did. It's going to be less about the nerdy model math, and it's going to be more about how we implemented super res on Twitch. Now, super res is really appealing to us on Twitch because we can run it on the viewer's GPU to improve their video quality for free. And this really enhances our bitrate ladder. We can go above what we typically offer, for which right now is 1080p, and upscale 1.5 times to 2K. We can go within our bitrate ladder to upscale 720p to 1080 for a viewer who is not able to achieve that on their connection speed, all the while potentially saving us a lot of bits. Now, since 2019, a lot has changed to make super res possible on the web. GPUs have gotten much faster and more expensive, and gamers, like what we see on the Twitch audience, tends to adopt them pretty quickly. Models have gotten faster, and most importantly, certain key web APIs have recently become available to make it possible. So earlier this year, we put together a team at Twitch to try it out, and we had a few questions. Could we achieve real-time performance, meaning for us 60 frames per second? Could we reach enough viewers on all the different GPU types we see on Twitch to make it worth their while? And last but most importantly, does it actually improve the holistic viewer experience? Meaning, when we run super res, do people watch more? So in August, if you were one of the lucky 10% of Twitch viewers on the website using certain GPUs during certain periods of time, you did experience super resolution. And this is what it looks like. And I hope this appears well on this monitor, but our algorithm isn't a miracle algorithm. It runs in real time. But you can see in particular, text is brighter and sharper and overall less blurry. We only target the Luma channel, but for those of you who have read the VMAF blog post, which I think we all have at this point, people notice brightness more so than anything else in an image. So we're going to talk about how we engineered the SDK to meet these performance goals and also protect the viewer experience while we're doing something fairly risky on millions of people's Twitch sessions. I'm going to talk about the Web SDK implementation, and James is going to talk about the WebGPU models and shaders and all that really fun stuff that I know nothing about. So let's talk about our performance goals. The first is that we want to upscale at least 720p 1.5 times to 1080p. We want to upscale each individual frame in under 16.67 milliseconds to achieve 60 FPS. And last but not least, we don't want to melt the viewer's GPU. We could create the best super resolution algorithm ever that turns 160p into 4K, but if it pegs the viewer's GPU at 100%, spins up their fans, makes their bedroom hot, and they turn off Twitch, then we failed to actually make a good product. So let's take a high-level overview of what we came up with. Starting from the left, we have a frame generator component that is copying frames from our media source extensions video player and inserting them into WebGPU in a process that we call the frame transformer. The frame transformer is running a series of WebGPU compute shaders and finally produces a GPU texture. We then render the GPU texture to canvas using another WebGPU compute shader. Keeping an eye on the performance and ready to hit the big red button is a performance monitor. So let's take a look at the first part of this system, the frame generator, and why WebCodecs. The reason is because WebCodecs and WebGPU play very nicely together. Hardware-decoded video frames already live in GPU memory. And the WebCodecs video frame object gives us a handle to that frame in memory, which we can then zero-copy import into WebGPU. Zero-copy is not free, but it is very fast. If we didn't have this kind of API, we would have to take the frame out of GPU memory, into CPU, and then into WebGPU. I tested out a very naive implementation of this on my M1 MacBook, and it took 4 milliseconds to pull a frame out of the decoder and into an array buffer. That is a quarter of our frame budget without even getting to do super res. So how do we generate video frames? And the most obvious answer is to rewrite your whole player to do WebCodecs, which we're going to do right after we rewrite the whole player in Rust. Today, we have a media source extensions player, and it does so much for us. MSC decodes video, renders video, decodes audio, plays audio, and it does AV sync. If we had to do all that ourselves with WebCodecs, we would probably be up here doing a talk about how to turn your MSC player into a WebCodecs player. So we needed something that works with what we have, and request video frame callback does exactly that. RVFC is an API on the video element that allows us to register a callback that fires when the next video frame is composited. And if we continuously register this callback at the source frame rate of the video, then we get access to every single video frame. Almost. RVFC has one big downside in which it can only run on the main JavaScript thread. And now for those of you who aren't JavaScript nerds, the main thread on JS is where everything happens that you don't explicitly put in a worker and where all things like HTML and DOM updates happen. On a website like Twitch TV, this main thread can get pretty busy. And when it does get busy, we can miss frames. And in our experiment, we saw an average of 2 to 3% of frames missed, which is not super bad, but higher than the 0 what we want. However, RVFC is good enough and cheap, and that's pretty much the implementation of it right there. So let's take a look at what we do with the frames after we've grabbed them. And now, like I mentioned before, James is going to talk much more about WebGPU and compute shaders and all that good stuff. But what I want to cover in my limited amount of time is how we've engineered the transform pipeline to maintain a high rate of performance. And the central challenge here is handling what you do when the GPU is too slow to upscale the frame within our frame budget. And our main strategy here is to skip frames. What we did is create a parallel pipeline to our SuperRes upscaler. And in this pipeline, we have a dummy upscale function that simply takes in the video frame, waits a configurable amount of time, and then just returns the frame. When a frame comes in to do SuperRes on, we race the real SuperRes upscaler with our dummy pipeline, whose timeout is set to our frame budget minus the time it took for the frame to arrive in this part of the pipeline. We then race the upscalers, and whichever one returns first, we render to the canvas. In this way, we're always able to maintain a high rate of frames, but it might not be doing SuperRes, or it might be doing SuperRes some of the time. So we've just created a new problem. And if the GPU is categorically too slow to do SuperRes, and we're using the viewer's GPU and showing them no benefit, then that's not a good product. And in comes the performance monitor we mentioned. Performance monitor is ready to hit the red button if something like low frame rate is occurring or a high number of over-budget frames. And it's a pretty naive algorithm right now. And like ABR, we need to balance sensitivity with aggression. We wanted to quickly resolve when the player's performance is poor, but not so aggressive that we're penalizing viewers and turning off super res when their GPU is undergoing just brief periods of contention. In the future, we're hoping to make new models which are smaller so that we can down switch to a faster model instead of just having a binary on-off. Lastly, one of the best things to do is to just never let bad things happen in the first place. And we just only allow list GPUs which we know work well. And our allow list is here on the right. We just did this with local testing, and NVIDIA 4, 3, and 2 series work well. AMD and Mac could well, AMD and Intel could work well, but we simply just don't have those in our office to test with. Now I'm just going to put it back all together and look at our nice filled out diagram and just quickly go over how the player uses the SuperRes SDK. When it goes to enable SuperRes, it doesn't immediately show it to the viewer. We instead do this process called scout mode, where we run SuperRes in the background to dynamically measure your runtime performance. We don't want to show it to you if you can't do it. Once you pass that process, which takes a few seconds, we show the canvas and hide the video element. If there is an error, we hide the canvas and show the video element. And this process is fast and imperceptible to users. There's no black flash in their DOM. You might be thinking, what about audio? And you may be dismayed by this answer. We do nothing about it right now. We just let the audio play back from the video element over the canvas. We know that we're only a frame or two behind, and in practice, we have not seen noticed that this is a perceptible difference, and viewers have not reported it either. So with that, I'm going to hand it off to James.
Cool. Thank you, John. Oh, we missed some uncovered topics here. Go for it,
yes.
John.
Please come talk to me more about really interesting things that I didn't get to summarize in my
We'll be
10
hanging
minutes.
out, and we love to talk about nerdy stuff, so,
Yeah.
you know. All right, I'm going to talk a little bit about how we did the compute shaders and how we do our video frame processing with WebGPU. So first of all, what is a compute shader? Not everybody here might be familiar with it. These are small programs that run on the GPU, and these are invoked as many, many threads within a work group that's dispatched by the CPU. So when you are calling your compute shader program, you're actually dispatching like a grid of work groups, and you end up with like the number of work groups times the number of threads. The nice thing about these work groups is they can share some resources like memory and barriers that are very useful for more advanced algorithms. The nice thing about this model of having work groups and dispatching in work groups is it gives you a lot of flexibility in terms of how we map our data to our computation. But there's a bit of a cost associated with that, which is that there's potentially less vendor magic that can be applied to it when you compare with something like a fragment shader. So what are we doing here? Obviously we're trying to upscale the video and ideally getting a better result than what we would get out of, say, bicubic or Lanczos. But when we started this project, we were kind of ignorant, and we surveyed the landscape of super resolution models, and we largely found that they were either too slow, as in we weren't going to be able to meet our real-time needs, or they would only do integer scaling factors. As John mentioned, we were trying to do 1080p to 1440p or 720p to 1080p, which is 1.5x or 1.33x, and you can't hit that if you're trying to use a model that only does 2x. Another thing that we found when we were doing this is that training our model actually makes a massive difference in terms of the quality that we get out of it. When we took pre-trained models and tried them out, we were blown away by how mediocre the results were. We ultimately landed on an architecture that looks like this. What you can see here is a bilinear upscale step, followed by a RGB to YUV conversion, which is somewhat unfortunate. But we take the Luma channel, run it through a small CNN, and that does a refinement step on what we've upscaled with bicubic, or bilinear. We use bilinear because it's cheap. So when we think about shaders and how to take that network and turn it into shaders, there's a few operations here that we can kind of group together and create a series of shaders out of. So at the end of the day, we ended up with 3 different shaders. The first is our entry point. This takes our lower resolution image, does the bilinear upscale, does the conversion to YUV, and runs it through the first convolution to be passed to our hidden layers. The second shader covers all of our hidden layers. This shader is invoked repeatedly depending on the number of hidden layers that we've configured. And it's a pretty typical depth-wise 2D convolution with the activation fused in. And finally, we have our exit layer that does the final convolution, takes the Luma channel that we've produced from that network, and combines it with the chroma channels that we separated out in the first step to produce the higher res image. So stepping back for a second to look at the, how this actually works with the browser. As John said, we import this as a GPU texture from a video frame with import external texture, which is a WebGPU API that does a zero copy import of video frames. But it's not entirely free because there is and this goes back to the unfortunate YUV from earlier, there's a automatic conversion that happens just before our network that is completely unavoidable right now. Chrome just inserts it, and we have to deal with it. And then once we have that, if we run it through our network, obviously, we end up with a GPU texture that we blit to the canvas. And this part is a little bit interesting. We chose, instead of scaling to the final viewport size, to blit it straight to a canvas that is the same size as the texture. And we allow the browser to ultimately scale to the viewport determined by the DOM. Because the browser can potentially use different scaling algorithms, and we want to match whatever the browser is doing. So when working with WebGPU compute shaders and working with trying to build like a neural network in WebGPU, there's a few things to keep in mind. Number one, you're going to get massive gains out of simply quantizing. Going to float 16 halves the memory requirements and doubles potentially the compute intensity that you can achieve, because certain GPUs can do vector instructions with that. You need to be aware of WebGPU's edges, and it's a little bit different than working with like CUDA or Vulkan or other GPU APIs, because it's in a browser, and so there's a lot of safety checks, and you can't get around them, but you can potentially do some things to reduce the number of times you interact with those safety checks. So you can amortize the cost of those safety checks over more compute or more memory fetches or whatever. Loop unrolling is something that I hope the Chrome team addresses at some point. There's nothing to hint that a loop should be unrolled. You just have to do it manually, and really hot inner loops can make a big difference in terms of your performance if those aren't being unrolled. And choose the right algorithms. There's a lot of literature out there on optimizing compute shaders, a lot of stuff on archive, on vendor documentation, and blog posts out there. If you're going to go deep on this stuff, do a lot of reading, do a lot of experimenting, and you'll get some good results. And speaking of which, results. We made it pretty fast. You can see on an M2 it runs in about 10 milliseconds. On John's 3080, it's about 7.5 milliseconds, and on my 4080, it's about 5 milliseconds. That's not quite as fast as I'd like it to be, but it's pretty fast. It's fast enough to hit 60 frames a second. And going back to the experiment we ran earlier this year, we saw more hours watched. I'm not going to reveal any numbers, but we're pretty satisfied with that result. And looking forward to the future, there's a few things on our radar here. Number one is WebCodecs. Obviously, if we rewrite the player in Rust, and then after that we decide to move to WebCodecs, we'll be able to synchronize the audio a little bit better, which will make some people in this audience happier. And we will not miss any more frames, which will make us happier. Next is cooperative matrices. Well, not next, but hopefully sooner than next. Cooperative matrices. This will give us tensor cores, if you know what those are, on NVIDIA GPUs. Warp matrix multiplication, which is going to be a lot faster. And then WebNN is an interesting new API, and I'm getting the red light here, so
Keep going.
I'm looking forward to WebNN because it'll give us access to NPUs. NPUs are starting to become more popular on new computers, and that is it.